Okay, so we're here and we're recording and we're looking at some fluorite stuff, and uh, I'm trying to explain some how this valency works with this fluorite because it's so easy to observe. So at first we did some experiments and we cut the fluorite in half, and once we did that, the fluorite itself started stealing electrons from the oxygen, and you're getting that white film on the fluorite, making itself pure again. It's turning into a pure state of fluorite. Now, what's happened is I think there was some pure spots of fluorite inside this deposit, and it was stealing some electrons from the lesser strong fluorites, and it was making itself pure in these little hot spots. And when these areas had lost that electron, it left little micro voids in there, and there was able to make some deposits of some slightly noble metals that were able to fill those voids, giving it this exposure of yttrium, is what they call it, is the type of metal that's in there. But they're volatile, and the reason it fits so well is the fluorine was trying to accept valence electrons, and there was only a certain few available electrons from the hydrothermal fluids that were able to fill those voids, and that's how you get those metals inside these deposits. All right, so what's happened is I believe this is called gneiss deposits, and it's from highly altered granite, and you get these really beautiful textures of gneiss. I think it's spelled with a Gneisen or something like that, and it's called a gneiss deposit. And what's happening is there's this highly altered granite, and what happens is there's a stage of cooling from the magma, and there's these cracks and fissures that occur from the contraction. And when these areas create these fissures and voids, this hydrothermal fluid is able to fill those voids and solidify as these deposits. And we get these really beautiful mineral deposits from these gases and these hydrothermal fluids that are venting into these voids and crevices. So what's interesting is we got this oxygen that's turning the fluorite pure. It's giving us this white film. But when we put a passivation layer, which means we block the ability for oxygen to attach, you get this almost black color that looks really rich. This is the two halves in comparison, and it's still the purple stuff, but there's no exposure, so the way that the light reacts with it, it's not able to be reactive, so we don't see that that hue, that purple or that glow. It's just sitting there cold, while this one is exposed to the air and it's hot and it's reacting, and just a gentle reaction state of oxygen. Now, what's cool about this is we can see that this is trying to gain electrons to become pure fluorite just from oxygen. But what happens when we force electrons into the fluorite itself? How quickly can it become pure? How quickly does it gain electrons during a reaction state? And we're going to show you that right now, how quickly that's done. Now, what's going to happen is before we get all this stuff going, we're going to look at this other mineral. And this little black mineral right here is mercury telluride. It's called coloradoite. And what's weird is this is on the right side of the periodic table, and it has 7 shells, and it's missing 1 electron to become pure fluorine. So it wants to become pure fluorine because that is the element that has a core structure of fluorine. This right here is a mineral, but it's a compound, and it's not a nearly pure element such as fluorite. This is a compound, and it has multiple elements that are compounded together. Now, the elements are tellurium and mercury, and both are stable at cooler temperatures. And they're also very volatile at hot temperatures or warmer temperatures, just above boiling point. And their volatility and their deposit that we're seeing, that they were in the earth at one point, and they vented up as gases, and on the surface there was these voids and fissures and stuff where these gases were venting, but it was really cool on the top. And as this mixture of gas was cooled rapidly, it solidified into a compound. And this compound is a mercury telluride called chlorodoide. Now, what's interesting about these guys is they're kind of more in the middle of the periodic table. They have really stable outer shells, but they're missing an extra electron. And what's happening is it's easier for these elements to lose an electron than they are to gain them. So what happens is when they are in a volatile state, they're losing electrons, and there's these gases that are formed. They're ionic gases, and it creates this instability where we get a vapor of just think of you're losing electrons. They want to float up because heat rises. The heat is going to the path of least resistance, and that is the coldest area. So the coldest area is going to be the path of least resistance, and the air is cooler than the earth because the earth is a solidified matter and it's reacting, so it's constantly under temperature. This right here, when we volatilize, it's going to take the path of least resistance, and the electrons are going to go, and because there's so many electrons all bound up into it, it's also going to want to volatilize the core structures of these noble metals that are inside of here. And they are very microfine. They're not really stable core structures, and they're able to volatilize at a certain temperature until they wind back down due to condensation or condensing, where they're able to come back. Well, the experiment that we're going to do is when these guys condense, we're going to show you how they can condense without a with a gentle reaction, where we slowly let it condense, and then we're going to let it condense rapidly in another element, which is water, H2O. And what's funny is in H2O, the hydrogen atom is more stable than the oxygen atom, and the oxygen is able to act as a donor atom and donate the valence electrons to the mercury as it's cooling down, because it's trying to gain its electron. Because remember, we volatilized the electrons because these ones like to lose electrons. And as it's gaining back its electrons, it gains an oxygen atom, and it forms a new compound called cinnabar. And cinnabar is a famous stone that they say is poisonous, but the Buddhist monks like to wear them as mala beads around their neck and wrists. That it's part of the earth, so that we can be aware of what it is. And it's not that dangerous, but it can be if you're breathing it like you are oxygen. So what we have to do first, before we get this reaction to show how fluorine quickly absorbs and steals electrons, and how slowly a noble metal that is volatile loses electrons, gives us this standard. And I was thinking we should call it the MILF standard, like mercury, intuition, ladder to fluorites or something. We'll just call it the MILF standard, and that's what happens. This is the first thing on my mind, so that's what I'm saying. So we're gonna bust this, and we got this little piece of mercury here. We're gonna bust the second piece. Yeah, we're gonna get a piece here. Come on. We'll get a nice piece of mercury. Almost. I mean, we can use a piece of what that black stuff. Oh, there it goes. Alright. Bear with me here. Okay. So that looks like a piece, kinda. This is the better piece. It's like more like gold oxide, so I don't know if you can see it. These weird little browns where they look like oxide pits. That's the gold oxide. There's several different types of gold in the world. There's a little piece. So we have a couple little pieces. We'll use these little pieces to show you what's going on. Okay, so this is my little heater stand right here, and bring this one up a little bit. Okay, and we're going to show you how quickly fluoride absorbs valence electrons. We're using heat as valence energy. Oh. Alright, got the gas on. We got a rock on the heater plate. Gonna get this torch going. Now watch how quickly it absorbs these electrons. It's becoming pure fluorite, just adding heat. I should have grabbed a little deal there. There's a little bit of purple. But look, it's already pure fluorite. We'll let that cool a little bit. We'll do a second one, just how quick it was. It's a little bit bigger piece, so it gives you kind of a little bit bigger standard. That was easy to add electrons to a smaller mass because of its volume. And when we have a larger volume, it takes a little bit more to add the several thousand electrons that we need to achieve pure fluorite. You can see how quickly it's absorbing the electrons. It's just taking them in and becoming a pure element. And it's taking this much longer because there's that much more, mass. So this is the molar mass percent is much larger than the small piece. But after some time, and it's been given enough electrons, you can see that it has become pure white fluoride. And that's how long that little bit much more took. So in comparison, we have a smaller mass percent. Its mass is smaller, and this mass was about 5 times more, maybe 7 times more. So it took 7 times more energies than it did to make this pure fluorite versus doing a smaller sample piece. But you were able to see how rapidly that these elements are able to absorb valence electrons and become a pure fluorine. And that's that white stuff, and it's kind of hot. It's still a little bit hot, guys. But you can bust it open, and it's hot. It's hot. You can see it's all the way through. It's pure, and need a little bit of hammer action. Oh. Whoa. You can see that it's white all the way through, and there's no more purple there. Now, that was a mineral on the periodic table that steals electrons for any reason from anything, because it's highly reactive to do so. Because it's such a stable element in the periodic table, though it is missing a energy to become a pure element. And we give it that little bit of energy and it became pure. So now we got this Coloradoites. Hold on. And what we'll do is we're going to take this little bit of water. See if we can get our heating going. And see how slowly this loses electrons for such a small piece of mass, because it has a stronger core structure. You can see it bubbling in there. And it's gold that's bubbling in there, but it's volatilizing because of that volatility that we were talking about, where that the other electrons force the core structures out, and they're hot enough they're able to volatilize. Have all this heat, and you can see it bubbling like a metal. But if you put it in the water, really really quickly. And condense it. It became red. I don't know if you can see that. That looks red. Let me see that. That is super red. And that became cinnabar. And it is still a strong element. It didn't turn into mercury, and it didn't disappear either. It took a lot of reaction temperatures, and because the counter reactions were occurring, where every time it tried to lose an electron tried to come back, and it caused a counter reaction. But when we condensed it very rapidly, we were able to add oxygen, and this created cinnabar, and we were able to make homemade mercury oxide that way. All right. Now, that was highly volatile, so we were seeing something in there under temperature, but we don't know how to capture that something that we were seeing. So here we go with, let's find another good piece of it. Does that look good? Or how about this piece? Yeah, there's a little mercury on there. So we're going to heat this up and let it cool slowly and see that it's not able to gain those valence electrons like it was from the water, and you will see that this doesn't turn red like it did. Hold on. Where did my lighter go? Oh no, it fell down in there. Hold on. And I got it. Kind of. Hold on. And I got it. Yes. Yes, no. It fell into a crevice. Okay, I got it. There you go. Now we'll do the experiment. Now, this is the same mercury telluride. We can give it the same heat. Get that same bubble action going before we let it cool. You can see a metallic luster under the temperature. It looks really pretty. Now, we'll just let this cool slowly, and then we'll verify by hitting it in the water. So because it's cooling slowly, we have a compound, and in this compound we have mercury and tellurium, and what's happening is as the mercury is trying to react, it is able to borrow the valence electrons from the tellurium and become metallic again versus an oxide. So what happens is the tellurium acts as a donor for the electrons, as the mercury is stealing the electrons from the tellurium. causing it to be stable, and it's making the stability inside this compound, where we're not seeing any red oxides. We might see a little bit, just a hint on that one side, but it's nothing like the red. Now, when we hit it with the torch again and we drop it in the water, we're going to get that brilliant bright red, because it's going to steal the electrons from the oxygen and not the tellurium. And what happens is that process of stealing it creates a new compound, because it wants to be metallic, but it can't be in its pure state when the oxygen is in competition with the mercury. So we'll heat this. It's really hot. And now we're going to turn it red into cinnabar. Okay. Now this is going to be drastic. You're going to be like, what the heck happened? Oh. How did it get so red? That way. And if you take a closer look, it's completely red all the way around when it remained black before. So those are different reaction conditions, and that is how we're able to make catalytic effects when we are bonding molecules, when we're doing chemistry reactions, when we're trying to make reagents. It's kind of the idea of how we are able to transform, borrow, and donate certain energies from these elements in Earth that we need to form new compounds, produce pure elements, and catalyze certain stages of a process that we want to achieve an overall effect in. So say something that reacts slowly, like this, is reacting much more slowly than the fluorine, and say we wanted to react this as fast as a fluorine, we may need some catalytic ingredients to catalyze the effect and timing on these achievements that we're trying to make as products. So that's my little documentary. This is I call it the MILF standard. It's the mercury intuition ladder to fluorite, and we can see the oxide layer and a passivation layer that is blocking the oxides. That's all it is it prevents a passivation layer, something that prevents a reaction from occurring. And we can use different things for different situations when we need passivation layers, like condoms and all those other things. But anyways, after all these silly elements, ingredients, and processes, I hope you enjoy. I hope you have a safe day and have a little bit more understanding about Earth chemistry and the minerals that we have. Kind of helps out. Now, say we wanted to steal all these tellurium, because remember the tellurium is our donor. If we wanted to steal all the electrons from the tellurium rapidly, we would crush these two up, the fluorite and the coloradoite, and we would put them in a reaction state, and this purple stuff right here, the less reactive fluorite, if we mixed actually these two together, we're going to achieve a very rapid reduction. We're going to achieve a very rapid metallic state, knowing how many electrons we need to steal from the less reactive element to produce it into a metallic state. Of ultimate achievement would be mercury. And we would do this in a volatile state, and we would need also a condenser chamber to condense the volatile mercury into a cooled down metal if we were to do that. Just kind of some ideas, something to plan for in the future, where the gold might be one of these days. If you ever get to exploring this specific kind of oxide ore, but I think you'll figure it out. Look how shiny that one is. Pretty cool, huh? You can see it's in there. So we almost got it. I almost got a whole bunch of it, don't we? Look at the size of that guy. It's a big, giant rock. All right, that might be. Thing weighs like a pound. All right, here we go. Have a good day. Love everybody. Later on, this is Mr. Starlight from Galaxy Miners. Over and out. Journey on to the stars. Peace be with you. Enjoy your vacation at Roswell. Adios.